Hello everyone. In this video, we'll discuss about AC circuits. It's a part of a chapter called Alternating Currents in Class 12 syllabus. In this, we'll discuss about if AC voltages were to different circuit elements, how the current and voltage will have some phase difference and all that kind of points. So now, general AC voltage will represent like this. E is equal to E naught sine omega t. Here E naught is called as peak value or maximum value. So now this AC source is connected to, this is a general representation of AC source. If this AC source is connected to any circuit element, then we have to find that corresponding current. Here we will introduce a term called phasor diagram. Phasor diagram that represents the phase difference between current and corresponding voltages, and for this always our reference will be voltage. So voltage will have zero phase difference with itself. That means our reference line voltage will take like this, and current, if it is leading, will show a graph ahead, and if current is lagging, will show that graph below this. So for phasor diagram, who is our reference point means voltage, so that its phase angle with itself will be zero. So now if AC is connected to pure resistive circuit, if it was given like this, AC is connected to pure resistive circuit, if AC is connected to pure resistive circuit, means it will be like this. We'll have a resistor. For this resistor, we connected an AC source. If R is the resistance and E is the voltage applied, which is E naught sine omega t, then current in the circuit will be equal to E by R, or that will be equal to E naught sine omega t by R. E naught by R will represent with I naught sine omega t. So this is current through the resistor at any instant of time. This is current through the resistor at any instant of time. And from this we can say one point, as this current is not having any phase difference with respect to voltage, because both we are having sine functions. That means the phase difference between current and voltage in pure resistive circuit is zero. Phase difference between voltage and current in a pure resistive circuit is zero. And corresponding phasor diagram we can represent like this. If voltage is in this direction, current will also be in the same direction. Suppose if they gave in a plane like this, if voltage is in this direction, current will also be in the same direction. And as both are sine functions, that sine curve also we can represent like this. If this is our voltage graph, that corresponding current graph will be like this. Both are sine functions. This corresponds to voltage and this corresponds to current. Current or voltage to time graph. So you can expect some questions based on this. And now we are having one interesting note point here with respect to this resistive circuit. if you are having a resistor that is connected to a DC battery, then DC battery means normal battery. If the voltage is E, or I can assume that as V, power dissipated across this will be equal to, if I is the current, it will be I square R. And if suppose the same, if it was given like this, if there is an AC source is connected, then power dissipated in the circuit, we have to take I RMS square R. So once we know I is equal to I naught sine omega t, so we can calculate IRMS like this. IRMS will be equal to I naught by root 2. From that you can calculate power dissipated uh, through that resistor if it is connected to an AC source. So from that you can find heat energy produced also by using I square RT concept. Here we'll use IRMS square RT. Then if AC is connected to pure capacitive circuit, this is our second circuit, pure capacitive circuit. Pure capacitive circuit. This pure capacitive circuit, if you are given like this, there is a capacitor of capacity C is connected to an external source like this. If that source is having voltage E is equal to E naught sine omega t, and the corresponding capacity of the capacitor is C, then charge on the plates of the capacitor at any instant of time, charge on the plates Q will be equal to C into V actually, but that will be E. We'll write C is equal into E naught sine omega t. So now if they asked for what is current, means current is nothing but rate of flow of charge dq by dt. So here C, E naught are constants, d by dt of sine omega t. So differentiation of sine omega t will be equal to omega cos omega t. So I'll write omega C E naught cos omega t, or the same equation we can write like this, E naught by 1 by omega C cos omega t, we can write sin omega t plus pi by 2, because sin 90 plus theta, it will be cos theta. Here this 1 by omega C, I can write that as xc sin omega t plus pi by 2. Here xc, which is equal to 1 by omega c, resistance offered by the capacitor, will call that as capacitive reactance. Capacitive reactance, we can write this as xc is equal to 1 by 2 pi fc. So if frequency increases, capacitive reactance increases. So that we'll have one graph like this between xc and, as they are inversely proportional to rectangular hyperbola. So it will have dimensions of resistance only, so that we can represent voltage by resistance as I naught sine omega t plus pi by 2. So that current in a capacitive circuit, pure capacitive circuit, leads voltage, as we got that as plus pi by 2. What happens means current leads voltage. So I'll write that point here. Current leads voltage by pi by 2. Current leads voltage by pi by 2. So you can represent this as a diagram like this. If suppose this is our voltage, so current leads means I can draw like this, plus pi by 2. Or else if suppose they gave like this in this quadrant, this is our voltage, So exactly perpendicularly we can draw current. It has to lead like this. And time varying graph, if this represents voltage, that corresponding current where voltage is 0, their current will be maximum and gradually becomes 0 and again becomes maximum and again becomes 0 and again it reaches to maximum value. Just we can think like this: if voltage is sine function, current will be cos function. So this kind of questions also we can expect based on the graphs. And then we'll have pure inductive circuit. So third circuit, it is about pure inductive circuit. If you are given like this, there is a inductor that is connected to an external AC source like this. Then that induced EMF developed in the inductor, we can write like this: that induced EMF developed in the inductor will be equal to E is equal to L di by dt, where L is the self-inductance of the inductor, E is the applied voltage. And from this, we can write like this: E naught sine omega t will be equal to L di by dt, or from this di will be equal to E naught by L sine omega t dt. So if we integrate on both sides, we'll get like this. On this side, we'll get I E naught by L into minus cos omega t by omega, or this we can write like this: E naught by omega L into sine omega t minus pi by 2, because if I can take minus sign as common, sine of minus theta will be minus sine theta. So minus sine 90 minus theta will be cos theta. So we'll get minus cos omega t. So I can write cos omega t like this. So now here this omega L will introduce a new term called XL, that is called inductive reactance, will be sine omega t minus pi by 2. So this XL is equal to omega L, or we can call this as 2 pi FL, inductive reactance, as it is directly proportional to frequency. We'll get XL frequency graph like this. We call this as inductive reactance. So it will have dimensions of resistance only, so that this equation we can write like this: I naught sine omega t minus pi by 2, that is I. So now from this we can give one conclusion that in a pure inductive circuit, current lags voltage, or we can write like this: current lags voltage by pi by 2, or phase difference is minus pi by 2. So once we know this, we can draw that graph like this. This is a voltage and this will be corresponding current. If they gave in coordinate system like this is our voltage direction, corresponding current will be like this, perpendicular to this. This will be I. And if we are having an AC source like this, then it lags. So we'll have graph starting from here. Initially it will be maximum, but it is lagging and becomes 0 and again maximum and again lagging, and again it becomes maximum. This corresponds to current, this red line corresponds to current, and that white line corresponds to voltage. And after this, I'll just give you some simple note points. So as we got like this, current is equal to voltage by resistance. We can write like this: resistance will be equal to voltage by current, and there is no phase difference between current and voltage in pure resistive circuit, so that resistance also we can represent in a phasor diagram with phase angle 0. And similarly this is for resistive circuit. And next we observe for capacitive circuit, current will be equal to voltage by capacitive reactance, or from this Xc will be equal to E bar by I bar, or that will be E of 0 by current is leading I of plus pi by 2. So I can write like this: E by I of minus pi by 2. I will bring this pi by 2 to the numerator, that becomes minus pi by 2, so that we can give one point like this: Xc bar will have a phase difference of minus pi by 2. See, they will not ask you as a numericals, but just if you remember this, you can solve some questions very easily. That's why I am giving this. And third point, we are having current in an inductive circuit will be equal to E bar by XL bar, or from that XL will be equal to E bar by I bar, and here E of 0, voltage will not have any phase difference with itself, but current is lagging, so that this will be E by I of plus pi by 2, and hence I can give one comment like this: XL will have a phase difference of plus pi by 2 with respect to resistance. So Xc lags, and hence current is leading in capacitive circuit. XL is leading, and hence current is lagging in pure inductive circuit. So if you will remember this, it will be helpful for next circuits. Yes. Our next circuit will be RC circuit. RC circuit. In RC circuit, we will have a resistor as well as a capacitor. RC circuit. Suppose there is a resistor and a capacitor. They are connected in series to an AC source. Then resistor will offer a resistance R, and capacitor will offer a capacitive reactance Xc. And here resistor, if it is having a phase difference 0, capacitive reactance lags. So this is Xc. As they are mutually perpendicular to each other, the resultant resistance here will give a new name called impedance. That impedance will represent with Z, that is R bar plus Xc bar. As they are mutually perpendicular to each other, its resultant will take like this. This will be the Z. That Z value will be equal to square root of R square plus Xc square. And if this resultant is making an angle phi, that angle you can find by using tan function. Tan phi will be equal to, if this is Xc, this will also be Xc. So tan phi will be equal to Xc by R. As it is below resistor axis, Z bar we can represent like this: Z of minus phi. And you can find cos phi also from here. This cos phi is equal to adjacent side by hypotenuse R by Z, and this is called power factor of the circuit. We'll call this as power factor of the circuit. And once we know Z value, they'll ask you about current in the circuit. That current I will be equal to E by Z, or that will be equal to E by Z of plus phi, or we can write like this, I naught sine omega t plus phi, where here I naught is nothing but E naught by Z. So current leads voltage by an angle phi. And how you will find phi means we are having two different cos function as well as tan function. Based on that you can find, and they may ask you to find what is impedance offered by the circuit, that will be Z. Okay, so here you can give one statement like this, current leads voltage by phi. So now we are having some interesting examples like this. Just look at this example. If you are given like this, there is a bulb, and bulb will have some resistance. It is connected to a capacitor. This is case 1, and now it was given like this. A dielectric is inserted between the plates of the capacitor. A dielectric of dielectric constant K is introduced between the plates of the capacitor. Then they'll ask you what happens to brightness of the bulb. Okay, so here if dielectric is inserted, we are having capacitance formula like this. C will be equal to K epsilon naught A by D, or that will be equal to K times C naught. So this is air filled capacitor. First case is air filled capacitor. Compared to air filled capacitor, if you are having a dielectric filled capacitor, capacitance increases by K times. If capacitance increases, capacitive reactance, which is 1 by 2 pi Fc, as C is increasing, capacitive reactance decreases. C increasing, so capacitive reactance decreases. If capacitive reactance decreases, Z, as Z, which is square root of R square plus Xc square, Xc is decreasing means Z will also decrease. So current in the circuit, which is E by Z, as Z is decreasing, current will increase. As current is increasing, power dissipated across the bulb, which is I square R. So brightness of the bulb increases. Brightness of the bulb increases. The same question they may ask you like this. If frequency is increased, if frequency is increased, so if frequency is increased, then as Xc is equal to 1 by 2 pi Fc, with increase in frequency, Xc decreases. If Xc decreases, Z will also decrease. If Z decreases, current increases, and hence in that case also, brightness of the bulb increases. Brightness of the bulb increases. This kind of questions we can expect based on our known concepts what we learned in our electrostatics, as well as in this chapter frequency dependence on capacitive reactance. And the next one is RL circuit. The next circuit what we learn is RL circuit. That means a resistor as well as inductor will be there. If suppose there is a resistor and an inductor, ideal inductor whose resistance will ignore here. So now, as resistance is not having any phase difference, inductor leads resistance, inductive reactance, so that resultant impedance Z will be equal to R bar plus XL bar, or Z will be equal to square root of R square plus XL square. As they are mutually perpendicular to each other, this will be Z direction, and this will make an angle phi. If this is XL, this opposite side will also be XL. So once we know Z value, you can find tan phi. Tan phi will be equal to XL by R. So here that phi is above resistance axis. So that Z bar will represent like this, Z of plus phi, or cos phi, or power factor cos phi will be equal to adjacent side by hypotenuse R by Z. Once we know power factor, we can find this current in the circuit. Current I will be equal to E of 0 by Z of plus phi, or this will be equal to E by Z of minus phi, which we can write like this: I naught sine omega t minus phi. This is I value. So current lags voltage by an angle phi. Currents lags voltage by an angle phi. So if they asked us to find phi, you can use this equation or this equation, and Z you can find using this equation. And corresponding phasor diagram, if it is for current, you can draw like this: E and I, that phase difference will be phi. And now here also we are having some interesting questions like this. Just look at this example. There is a bulb and an inductor connected to AC, and for this inductor initially air core, so air is the core, that means inductor we can keep any ferromagnetic core, and later in the second case, this is case 1 where air is the core. Now in the second case, for the same inductor, a ferromagnetic core is filled. Case 2 is ferromagnetic core. Then what happens to brightness of the bulb in the second case? For this, self-inductance of a coil, we are having one formula like this: mu naught n square A by L, where L is small l is the length, n is number of turns, mu is the permeability of the medium, and A is cross-section area. If it is ferromagnetic core, then we will get mu r mu naught n square A by L, so that this will be greater than L. So as L is increasing, inductive reactance, that is omega L, inductive reactance also increases. If inductive reactance increases, Z in the circuit, what is Z formula? Z will be equal to square root of R square plus XL square. As XL is increasing, Z will increase. So current in the circuit decreases. Current in the circuit decreases, and hence brightness of the bulb decreases. So this kind of questions we can expect, and the same example what I quoted in the previous case, that is in capacitor case, I will quote here also. If we are having a bulb and an inductor, if the frequency increases, if the frequency increases, then XL as it is 2 pi FL, as frequency increased, XL will increase. So Z will also increase. As Z increases, current decreases. So in this case also, with the increase in frequency, brightness of the bulb decreases. Brightness of the bulb decreases. So this kind of questions we can expect. And one more example will be there like this. Suppose there is a coil. If it is not ideal coil, will have both resistance as well as inductance. When it is connected to a 12 volts DC, then the current observed in the circuit is 4 amperes. And when it is connected to an AC source of 12 volts 50 hertz, if it is given like this, this will be RMS voltage. Then current in the circuit is 2.4 amperes. Then they'll ask you find inductance of that inductor. Find inductance value. So from first case, as current is there, voltage is there, we can find resistance, that is 12 by 4. It is 3 ohm. And as we are having RMS voltage and this current will be RMS current, in the second case you can find that impedance, it will be 12 by 2.4, or else you can write 120 by 24, so that this will be 5 ohm. But as it is a inductor coil which is having both resistance and inductive reactance will be there. So Z will be equal to square root of R square plus XL square. From this, XL will be equal to square root of Z square minus R square, or that will be square root of 5 square minus 3 square. So XL will be equal to 4, which is equal to 2 pi F into L, or from this L value will be equal to 4 by 2 is nothing but 2 by pi into F. F is given as 50, so that this will be 1 by 25 pi Henry. This kind of questions also we can expect in the case of inductive circuits. And then now we'll have one more point like this: power in an AC circuit. As of now, we discussed about 5 different circuits. Power in an AC circuit. So if suppose this is a voltage line and current can lead or current can lag. So if suppose that phase angle is phi, I can resolve this into components. Component in the direction of voltage is I cos phi. Component perpendicular to this will be I sin phi. Then that component in the direction of voltage, if suppose this is E RMS value, definitely this will be I RMS value, and so that this will be I RMS cos phi and this will be I RMS sin phi. The component in the direction of voltage is I RMS cos phi. Then that power dissipated in the circuit will be given as, or average power we can write like this, that will be ERMS into IRMS cos phi. The same equation ERMS into IRMS into cos phi. This is one equation what we have to remember. And the other equation will be like this, E naught by root 2 into I naught by root 2 into cos phi, which is equal to E naught I naught by 2 into cos phi. And the same equation we can write like this also, ERMS into IRMS is nothing but ERMS by Z, and cos phi is nothing but R by Z. So that this will be equal to ERMS square by Z square into R. And the same equation, this is also important, this is one format. And the same equation we can write like this, ERMS is nothing but IRMS into Z into IRMS. So cos phi is nothing but R by Z. So Z gets cancelled. So that this will be equal to IRMS square R. So all these are different formats of power dissipated in an AC circuit. And here this IRMS sin phi, it is not contributing to power. So that's why it is called as wattless current. It is called as wattless current. And if phi is equal to 0, we'll call that as pure resistive circuit. For pure resistive circuit, cos phi will be 1. So power factor is 1. As power factor is 1, power will be equal to ERMS into IRMS. And similarly, for inductive circuit or capacitive circuit, phi will be either it can be plus pi by 2 or minus pi by 2. Phase difference for capacitive or inductive circuits. Then this cos phi will be 0. So power factor for pure inductive or capacitive circuit is 0 and power factor for pure resistive circuit is 1. So that there will be no power loss in a pure capacitive or inductive circuit. So that's it for this video. I hope you all enjoyed this video. Just write down a notes while listening this video. It will be very helpful for you. Please subscribe and share to your friends. This is helpful for both JEE mains as well as NEET aspirants. Progressive physics learning profile. Have a great time.